And because of this, they have less efficiency also, because they're not very well developed. So if you can, I recommend you to use step-down voltage regulator, which they start from a higher voltage and then they go down to a certain voltage. The last kind of voltage regulator that you can have is the most flexible one. It's quite useful because it can take care also of noises or oscillation that you have in your power supply. We are talking about step-up, step-down voltage regulators. So in this case, they will take as an input a range of voltage. So this means, for example, they can take as an input from 3 volts to 10 volts, and then they can give you as an output a fixed output, which is inside this range. So in this case, for example, 5 volts. So let's say that you're powering your device using a battery. No? You know that the battery will discharge over time. And this means that if you have a huge discharge of the battery, which means if you have, for example, a battery that gives you 30 volts, then maybe the battery can go down up to 20 volts, for instance. This means that these step-up, step-down voltage regulators can work all the way through this range. So they are quite stable and useful. Of course, the drawback of this one is that they will be more expensive. So for instance, this one that are pictured here, they are from Pololu, and they are quite expensive, but also quite good. So they have, like, for example, a lot of step-up, step-down voltage regulators. So the other parameter which you can look for a voltage regulator is the amount of current that they can transmit to the load. So you have 3 parameters for the voltage regulator. One is the range of the input voltage. So for example, one voltage regulator works from 12 to 24 volts, let's say, okay? Then there is the output, the voltage that we have as output, that is fixed. Maybe it's 5 or 6 volts or 7, whatever it is. And then you have the current that actually the voltage regulator is able to output to your device. So these ones on to the right are able to work up to 1 ampere, 1.5 ampere maximum. Instead, these Pololus, they are working with some 100 or milliamps. So for example, they work for 500 or 400 milliamps maximum. So they are not very strong as the other ones here. The difference between then these other 2 kind of voltage regulator is that these devices, they look like a transistor, and they are quite stiff, but they need some additional electronics to filter the input and the output voltage. You can think about using the decoupling capacitors, as we were talking the last time. Instead, these ones that they come from Pololu, they have these decoupling capacitors already on board. So this means that they are already filtered from the suppliers. So when you buy these ones, you don't need to use any additional electronics to work with them. Okay. So I use sometimes voltage regulators. I use, for instance, one of those in my drone because I wanted to give power to the microcontroller, which works at 5 volts, from the battery of the drone. And the battery of the drone was giving me 12 volts. So I needed to have this step-down voltage regulator. I also made some Internet of Things modules, which you can attach, for example, to the wall. And the microcontroller of these modules, they work at 5 volts, while the Wi-Fi module, which is the ISP8266, works at 3.3 volts. And then I needed to have this kind of board here. I will show you briefly the way that you can make a more complex power converter board that I also made for myself during my Fab Academy. So here is my repository about my board, but if we go on to the bottom, I also made this simple board, which was able to give me as output 3.3 and 5 volts, so I could choose the output that I want. And then as an input, I could give to this board fixed at 9 volts or 12 volts, either. So in here you can see the board, and I added some decoupling capacitors as well here to stabilize the power afterwards. So maybe I can also show to you the way that I did it. So in this case, I'm using 2 voltage regulators. Yeah. So one for 3.3 and one for 5 volts, because actually these voltage regulators, they give you only one output. So in case you want 2, you have to combine different of those. So in this case, one is 7805. So this 7805, guys, it's like standard choice for voltage regulators. It's very common, this one.
Is it a MOSFET?
No, actually, this one is a voltage regulator. It has, so they work somewhat similar to transistor, MOSFET, and so on, but their dedicated function is to be voltage regulators. So they have inside transistors and so on, but it's a specific device. This is called 7805. It's very cheap, this one. So you can buy for 35 cents or even less. It's very common one. Everybody uses it. Here you can see, for example, this one is the input voltage, this one is the negative, and this one is the output that you can have. This one, it's quite powerful, gives you maximum 1.5 amps. So you can have some powerful devices.
We have some, Daniele. We bought some already, but they look more like the ones in the Arduino Uno board. You know, they do the same thing, but the design is a bit different.
So remember, guys, that all of these components, they come in different packages. For instance, this one is the true hole package, but of course you can add also the SMD package that you can use. The only difference, you have this one, yeah, okay. So maybe I can show to you the way that I use this. It's here. So for instance, I created this Wi-Fi module here. You see? So this Wi-Fi module has basically the main microcontroller boards, which works at 5 volts. And then it has this Wi-Fi module over here, which works at 3.3 volts. So I was powering everything using a battery, which gives me, I need to wait. Yeah, okay. What does it matter?
Can you go back 20 seconds? Can you repeat that, please?
Of course, yeah. Okay. So this is just an application example of what I did with voltage regulators. So let's briefly analyze this simple module here. I have on the back this 9-volt battery. Okay, this 9-volt battery goes to the power board, which has 2 voltage regulators on it. And the 5-volt voltage regulator was giving power to the microcontroller board here, because this board needs 5 volts. And the other one, this one on the front, which is 3.3, was giving power to the Wi-Fi module, which works at 3.3 volts. So this is an example of one unique input voltage, and then you distribute the different voltages to different devices or your application. So you can think in your case, for example, that you have, I don't know, somebody of you is doing this dryer for the fruit, no? Maybe it needs certain voltage for the heater, certain voltage for the electronics, and so on. So you can find useful this kind of devices eventually. Okay. So this one from Pololus, this Pololus voltage regulators. Okay. There are a lot of different kinds of these voltage regulators. There is even one which is possible to regulate the output. So through, for example, this trimmer here, you can say I want to have 5.5, I want to have 4, I want to have 3 volts as output, and so on. And actually, there are also other kind of voltage regulators which are similar to this one. So they look like through hole, they look like MOSFETs. But then playing with resistors around them, you can actually change the output of the voltage. So you have different ways of doing it. Actually, the one from Pololus is quite user-friendly because it has this trimmer, and then you can use it. So guys, more or less, that's it about the voltage regulators. I recommend to use them only if it's strictly necessary to do so, because remember that they represent a waste of energy. And if you use batteries, they're going to waste the energy, of course, of the battery. So the battery life of your device will be shorter if you use them, okay? And don't forget, guys, to measure the amount of current that you need for your load. For example, I know that a board with a 328P maximum consumes 40 milliamps. So if I have 1,500 milliamps, so 1.5 amp, it's going to be perfectly fine. But if I'm going, for example, to power up the heater, which needs maybe 2 or 3 amps, then this one is not going to be enough. So you need to check this specification. Okay. So guys, more or less that's it about voltage regulators. Another application maybe that I can just tell to you is that I was looking away on how to charge a big supercapacitor or how to charge a battery from a low voltage, and then I was using a step-up voltage regulator for this. So I was having a small generator giving me maybe 1 or 2 volts, and then I wanted to charge a battery at 5 volts. And because of this, I used a step-up voltage regulator. Okay. Guys, questions about the voltage regulators?
Yeah, there's one.
Yes.
So in the image on the bottom left.
Can you hear him?
Barely.
Okay, yeah. So the image on the bottom left that has there's 2 small circuits and then the voltage regulator.
Yes.
So the voltage regulator is the thing that looks like a transistor, and that's the circuit that they connect to. Is that correct?
You mean this one with 220 or this one with 5410?
Yeah, so there's 2 circuits and then a voltage regulator. But what's
Actually, you know that to switch the voltage, you need several things. So for step down, you can imagine that, for example, a simple transistor would do it. Because maybe you open the transistor for half or you vary the resistance and then you have less voltage. That's okay. But for example, if you need to increase the voltage, then you need some coils. You need some coils and some magnetic fields. And then you know how a transformer works, no, more or less. And you have 2 different coils depending on the coils that you have and so on. But then these boards are even more complex because they have, for example, protection for short circuits. They check they measure the maximum amount of current that they're giving, and then they shoot off. So all these surrounding electronics that you see here, for example, this small chip and so on, are all these small components that are needed to do these functionalities. So this can be maybe a sensor, or can be an array of MOSFETs, or can work together with this coil. I need to look the data sheet and the schematic of this Pololu to answer you. Yeah, but these ones that you have here on the right, they have everything embedded inside.
Okay.
So this means it's just a small package. Actually, here you can even see that they have more pins than 3, more than input, output, and ground. You know why? Because these other pins are used as controlling pins. So you can say, for example, if I send logic level high to the pin number 12 here on the breadboard, or if I send logic level low, I can switch off and switch on the voltage regulators. So those are just additional pins for controlling them, if you are wondering why we have additional pins here. By the way, I tested a lot of those on my drones, these Pololus, and I have to say that they all were killed. So they are quite fragile for me, these ones, at least the application that I tried. Instead, this one on the right, they're much more stiff for me. They can stand up maybe up to 150 degrees before blowing up, and so on. So we can look maybe again the data sheet. Yeah, for example, this one stands up to 125 degrees. This one that is SMD, maybe you have this one, Luis.
Yeah, we have this one. Then we have the SMG one. Daniele, can you also, since you're already in your page, show quickly your quadcopter? There's a video of it. Maybe just show the video.
You want to show the video?
Yeah,
Okay.
quickly, because then they can know what you could share as well.
Can you see the video from a screen?
Yeah.
Okay. So I will talk over it. This one was the first test. But this one, wait. It's not the, sorry. This one was the video, sorry. Okay. So guys, this one was the first test that I did, and was the first Fab Lab drone in the Fab Lab history to take flight. They tried in 2014, but they didn't manage to fly. It was in Barcelona. And this one was the first time that also we were flying. So we were inexperienced pilots of drone. And that was it. We just stopped it because we were unsure that this was good. Then, guys, I found the perfect formula to make a Fab Lab in the drone. I was flying with a cup of water on top of the drone. And this video is I'm using Neil. All the time that Neil meets me, is keeping telling people, this guy was flying with a drone, with a cup of water. Okay. And then I was also having a smartphone on board the drone, and I was able to send through internet to WebSockets the data of the sensor. So I was having sonar sensors. So while the drone was flying with all this equipment on board, I was able to transmit this data to another smartphone through the 3G connection. So this means that this connection can work like everywhere. I don't know if you can also hear the sound. I don't think so. No, okay. Yeah. You can just look the video. And here is the data being received from the drone. So this is the level of the sticks, the telemetry data, and all the information. Yeah. And the drone was also able to fly with all this equipment, of course, on board. So then here are some tests about the autopilot. So I can switch off with a signal the pilot, and then there is like an electronics board that takes care of controlling automatically the drone. This is all the data of the drone. You can see this one is the drone on a pile of wood, and then when I was going to the side, the drone was detecting me and was going far away from me. This automatically. So you can find this functionality nowadays in the market because DJI and Typhoon have implemented them in the commercial drones. So now even if you have two side obstacles, the drone was going 45 degrees away from the obstacle. No? Here you can see the autopilot. Now it's automatically driven. Now you can see the first error of the autopilot because there was a error in the code. By the way, this one was the first test to avoid the wall. So you go near the wall and then you can. The drone automatically moves away from the wall. In that case, here you can see the ralenti of the. Yeah, which was fast enough to do it. But nowadays, guys, this one, it's commercial. So when I did it, it was not commercial, but now it's commercial. So I don't have any more the uniqueness of it. No, so you can see here. My friend Gianluca was trying this with a helmet to make sure that, yeah, you can see. Yeah, okay.
Very cool, Daniele. Very cool. Sei grande.
Okay, thank you very much, guys. By the way, if you want to look it, it's all open source, of course. You can download all the informations. This was the microcontroller board that was used, for instance. And here you can see a little bit more about the connections and the traces and so on. And this board at the beginning was using also a voltage regulator, but was blown up because the battery is quite powerful. Too much current was passing through it, and then some traces were exploding, like here. And the drone was falling down because of this. Okay. Guys, if you have questions, we can make also lectures about drones or anything that you like, no problem. Should I continue back with the lecture while we finish? Okay. So here. So I will go on. One moment. Okay. So guys, the core of our board will be actually our microcontroller, which is having a lot of micro components inside. And actually, you cannot see it from outside, but inside there is like a small town, a small city with a lot of small peripherals and dedicated devices to make the microcontroller work. You can think about of a microcontroller as a very small computer. So it's an embedded computer. But the difference between the computer that you have in your desk or you have the laptop, for instance, and the microcontroller is that everything is embedded inside the microcontroller. What does it mean? If you open your laptop, you can still find the hard drive, the CPU, the RAM memory, the network card, the display. They are all separated devices that you still have in one case, but they are all separated devices. In the microcontroller, all these devices are inside the plastic package of the microcontroller itself. So you're not going to see them. So if you want to make like one-to-one comparison between the microcontroller and the computer, you can still see that inside the microcontroller there is the CPU, which is used for mathematical calculations and so on. And then there is the hard drive. In this case, we don't have the disk or the solid-state drive. We have the program memory, and the program memory has a very limited amount of space. So if in the computer we can have terabytes, in the microcontroller we're going to have kilobytes. Okay. The same is true for the RAM memory. So nowadays we have, I don't know, gigabytes of RAM memory. The microcontroller has key of RAM memory. For example, the 328P has 2 kilobytes of memory. So then in a similar way of the computer, we have, for example, the network cards or network peripherals. So in this case, we can see that we have the serial card and the E2C card, so the dedicated hardware for this. And then we have also some generic ports. So in the case of the computer, of course, we have the USB ports, but in the case of microcontroller, we have digital ports. With the digital ports, we can easily send signal to the outer world. So we can send, for example, logic level high, logic level low, and so on. And then we have also a special device which is used for sensors, which is the analog to digital converter. It's a device which takes as an input analog signal and gives to you a digital number. So for instance, in the 328P or in the Arduino, this one works between 0 and 5 volts. And this analog signal is sampled using 10 bits, which means that you have 1024 different values. So if you have 2.5 volts given as an input in this analog to digital converter, you're going to have 512 as value given from the analog to digital converter. Okay. We have also some other special devices which are used to generate pulse width modulation signal. So you can have square wave signal going out from the microcontroller. We're going to see this in the next slides. And we're going to have some timers. So you can actually measure the time in the microcontroller. And this is possible because you have the oscillator, which we were talking in the last lecture. So this oscillator will give you a precise indication about the time. Okay. And then last thing that we have is a special memory, which is called EEPROM memory. So all the time that you upload the code in your microcontroller, this code is going to fill in the program memory. So when you program in your microcontroller, you are going to delete all the content of the program memory, and you're going to write in this memory your program. Instead, you have this EEPROM memory, and this EEPROM memory will stay fixed even if you program this program memory. So this EEPROM, it's useful in case, for example, you have to upload a firmware for 3D printer or for CNC, and you want to keep the settings in a different memory. So you keep the setting in the EEPROM, even if you write again the program memory, the settings are still in the EEPROM. So if your microcontroller is acting in a weird way, and you don't know why, is also because maybe you forgot to delete the EEPROM. So to delete the EEPROM, you can just use a sketch from the Arduino examples, or you can write by yourself a software to delete it completely. Okay. Yeah, then we have the reset button. The reset button is like the reset button of your computer, guys. When you press the reset button, you are going to restart your microcontroller, basically, and the power supply, of course, how to give the power. So just to give you a physical sample of how a microcontroller is done, all these components which are in this schema here are represented by these different areas in the center. So the pins that you use to connect the microcontroller are quite big in comparison then to the sides and to the thickness of the transistor here. So it's like jumping into a micro world. Okay. So also the microcontroller, they have different kind of packages. You can find them with through-hole packages. So for example, the Arduino Uno has this through-hole package, and basically this means that you can change the microcontroller in case it breaks. But then you have also these SMD packages. Of course, when you solder those, it's very difficult to remove them. And the main difference between them, guys, is about the space that they take, because actually this small one here is the same as this long one on the right. For instance, they have the same logic. It's just the package that is different. So, guys, what's the use case for the microcontroller? So, why we need to have this embedded computer? Because sometimes we need to accomplish with several different small tasks. They can be complicated or simple tasks, but we need to do this in a device which is small, in a device which is portable, in a device which doesn't need all the computational power of a computer. So when you go to the supermarket, guys, and the door is opening automatically in front of you, this is managed by a microcontroller. And the super easy task that this microcontroller has to do is to read from a sensor if there is somebody in front of the door, and if there is somebody in front of the door, send the signal to the motor to slide the door. So more complex microcontroller can be found, for example, into the ECU of your car. So one of these microcontrollers with more megahertz is actually managing, for example, the amount of fuel that you are going to inject in your cylinders according to the RPMs of your engine, on the throttle, for example, and so on. So it's more complicated, but still it's a microcontroller. So all these kind of small devices, for example, if you have a fixed phone, it's going to have inside a microcontroller. If you have a drone is flown by a microcontroller. If you have a toy car, there is a microcontroller on board. If you have a stereo system, there is almost likely a microcontroller along with other components on board. So you can now easily understand what's the meaning on this. The other comparison is, because all the components are embedded inside this small space, the performance of this device, it's way lower than the performance of your computer, guys. Okay, so here we're talking about 16 megahertz, and the computer works at gigahertz, of course. You have gigabyte of RAM here, you have 2 kilobytes of RAM, and so on. Also for industrial machines, if you think about how the Ultimaker works, the Multimaker has a microcontroller on board, which reads the G-code and moves the axis. Your big CNC machine that you are going to work today, it's having a microcontroller on board. It's attached to the computer, but it's the microcontroller which manages the motors on a low-level manner. The other difference is the real-time constraints that you can have using a microcontroller. Because when you have a computer with an operating system on board, you have, like, I don't know, 20 tasks running at the same time. So if you want to have an answer given in exact time, so after 1 second I want to move a motor, this one is not the task from the computer, it's the task from a microcontroller, because the microcontroller has a single execution flow, and then you can have real-time embedded control into it. So in case it's critical for you that, I don't know, the door of the airplane opens up after 1 second that you landed, or something needs to be done in a specific time, you must use a microcontroller, guys, and not a computer. So a low-level device, which is able to work with reality. So to a microcontroller, you can connect sensors, then you can connect output device, so you can drive motors, you can drive lights, you can drive, in your case, for example, heaters, you can drive any kind of actuator. With a microcontroller, guys, you can even connect to older microcontrollers, or you can use networking device to connect them to internet. They have general purpose functionalities, and you can program each time the microcontroller to do something different. Okay. So I guess I annoyed enough you about microcontrollers. You can tell me if you have questions about it. Otherwise, I will go on with the microcontrollers. So this one that we're going to use for Fab Academy, they have 20 megahertz maximum execution, and they have quite limited flash memory. If you like, there are a lot of 32 bits platform, and Neil is going to show you some of those as in the last lecture. And then with these 32-bit microcontrollers, you can do more complex stuff. Yeah.
Just reminding you what we have in our lab. We have the 44, the 8044. We have the 8085, and we have the 80 mega 32U4.
U4?
Yeah, these are the three boards we have, the microcontrollers we have.
Okay, so Louis brought to you a very special microcontroller because, for instance, so depending on the kind of microcontroller, you have more or less functionalities. You must check them out before you want to use them. So the ATtiny44 doesn't have the serial port. Okay, and the serial port means that it's going to be hard to communicate to other microcontrollers. Okay, if you take the 328P, the 328P is going to have the serial port, so the hardware serial port, so it's easier to communicate. Also, the Atani44 has 4 kilobytes of flash memory. The 328P has 32 kilobytes of flash memory, so it's quite more. And then this 32U4 that Louis bought has also a special hardware inside, which has implemented the USB port. This means that you can connect this microcontroller directly to the USB port, and you can communicate using the USB port to the computer. Okay, so different microcontrollers, they have different functionalities. Before you're going to choose the one that you want to solder for your final project, you must first list all the functionalities that you need. I need to drive 7 motors, or I need to drive 1 heater and 3 motors, or for example, I need to have analog sensors, or I need to have serial communication between 2 microcontrollers. So you must first design your final project and estimate and list all the functionalities that you need.
Yeah, it's maybe overkill, but it's nice to tell them about the communication between microcontrollers.
Yeah, now it's the next slide.
Great.
Yeah, next slide. Guys, other questions about the microcontrollers? Okay, we can go on.
Wait, no, there's a question.
Yeah.
80 tiny 44, 84, and then the 80 mega 32U4. There are 3 examples. I mean, will they cover most of the applications that we generally will come across? Are they like the most common ones, or are there other common ones that are,
So these ones are quite the most one. You have more or less all the functionalities that you need for the scope of Fab Academy, of course. So we can have a brief look, if you like, just to have a comparison between them. So if we take, for example, the Atani44 or the 84. So first of all, what does it change between Atani44 and 84? The name indicates the amount of flash memory that you have on board. So the Atani44 has 1 kilobyte of memory. The Atani84 has 8 kilobytes of memory. So if we take the data sheet here, we can read this in this basic information thing. The other difference between this and the...
Sorry, that we have a very bad short interference.
Yeah, you have to repeat?
20 seconds.
Yeah, of course. So the first difference between the first 2 microcontrollers that you told me, so you told me about the Atani44 and the Atani84, okay? No, wait, or maybe you can repeat because was far away.
No, just one thing. So the 44, actually the 44 and the 84, their package is similar. It's actually
the same. No, it's the same.
But what we have the 44 and we have the 85. Which
is sorry. Okay, perfect. Yeah, okay. So the main difference between, let's take also the 85 then. Yeah. So guys, of course, the package of these two chips is different. I will show you now the difference. So let's talk about the main difference is the memory. So the Atani 85, okay, has 8 kilobytes of flash memory. So you can upload the program which is maximum 8 kilobytes, which means 8,000 bytes. The 44 instead has 4 kilobytes of memory, so it's half, so maximum 4,000 of program code. The other difference is in the package, because actually the Atani 85 has a smaller package than the Atani 44, and this means that you have less possibilities. So if we look the pinout of them, maybe I can increase the size of the image. This one, okay. So let's have a look to the pinout of this one.
That's a funny thing, because the 85 is smaller, it's exactly half the size, but has more flash memory than the...
It's a weird thing. Actually, this depends on what you buy, because if you see here, we have Atani 25, 45, and 85. And 25 has 2 kilobytes of memory, 45, 4 kilobytes of memory, and 85 has 8 kilobytes. But this is true also for the 24, 44, and 84. So basically, the last number, this 4 and 5, what does it change, is the package. So you can have the same amount of flash memory, but with different packages. So in this case, would have made sense to buy the 85 and the 84 here. So it's actually the same. For the sake of the programming steps with the Fab SP, it's better to have the 44, then you don't have to change anything. In case you want to program the 84, you just have to change the signature of the chip. So you can actually program it, okay? So let's have a look to the pins that we have here. So if you look at the 85, it's ultra limited, guys. So first of all, 2 pins are dedicated to ground and VCC, of course. So here we have 8 pins minus 2, so we have 6 pins. Plus 1 pin needs to be dedicated to the reset, guys. So also this pin for the reset can be used in another way, but still needs to be used as reset when you program it. So then you have even less, then you have 5 pins. Of these 5 pins, guys, if you want to have the external crystal to have up to 20 megahertz, you have to use other 2 pins. So these ones and this one for the crystal. So now comps that have only 3 pins free, and these 3 pins free, guys, I use, you know what, for programming, because it's MOSI, MISO, and SSK. So it's really, really limited. You don't have serial communication also, and you don't have but you have E2C at least. So you have SDA. By the way, so this one is quite limited, guys. And you have also limited pins for the ADC, for the analog converter. You have 1 here, 1 here, and 1 here. So guys, unless your application is really basic, don't use the Atitiny 85. Okay? In this case, we don't care about the double of the memory. We care more about what we can do with this, because it's very limited. If we go to the 84, instead, we can see that the 84 has more pins, actually the double of the other one, okay? And then still 2 pins are reserved for VCC and ground, of course. 2 pins can be reserved for the crystal, XL1 and XL2. But then, guys, you have plenty of other pins to do whatever you like. So this one, it's well suited for, let's say, more generic applications, but still, guys, you don't have serial, and you have only 4 kilobytes of memory on board. This 4 kilobyte, guys, will limit you, for example, if you want to use a display. It's very hard to use a display with only 4K of memory, because then you need to use the libraries, and each library will use some memory. So this one, guys, it's really limited memory-wise. If then we take the 32U4 has 32 kilobytes of flash, which is quite more. And let me see if I can find the datasheet for it. I guess it's this one. So this one is a data sheet of the 32U4. And we can see that this one has the USB 2.0, as I was telling you, integrated. And this one has 32 kilobytes of memory. But another thing, guys, is the RAM memory. So this one has 2.5K RAM memory. Guess how much memory do we have here? I don't remember by heart, but I guess it's really limited. So guys, you have 512 bytes of RAM memory. So half K of memory in this device. So it's really, you can imagine what you can do with maximum 512. So already, if you want to work with a bitmap, or if you have a string text, so each character of the string is going to take 1 byte. So you can have really limited amount of memory in this, guys. Okay? RAM memory. And this one instead is 2.5K, so it's much more. But if we look then also to the pinout of this one has many more functionalities. So first of all, it has, of course, VCC and ground. Then it has D+ and D-, which they are used for the USB connection. And of course, it has also the serial communication, which was not included. This one is this one, TX and RX, guys. Okay. So with this one, guys, you have enough power, enough memory to more or less run all the applications that you like. Of course, you can even have bigger ones if you want to have more memory and so on, but then it's up to your application. So if you really need to have more power for your project, more input, more output, then it's wise to go to another microcontroller. Otherwise, I would like to let you stick with these ones that you have. Also because it's going to be difficult to learn how to use them, and these ones still are quite simpler. Okay, that's no problem. Should I show some more complex one? Or it's fine? I think it's fine for me for you. I can also show complex ones if you like, no problem. Okay. So, okay, questions about the microcontrollers? Yeah, no problem. I can actually explain to you even the meaning of all of these writings that you have here, okay, one by one. So we can go here. So this AVCC and this RF are used from the analog to digital converter to have a reference on the voltage. And I recommend you to connect those to 5 volts or to VCC. Ground goes to ground, of course, okay? And then when you see here, you have, for example, PF0, no? Or for example, PC7. You will see that all the generic purpose pins, they start with P, okay? What does it mean, this P at the beginning? This P means port, okay? And then the second letter, for example, F or C or B, this means that we have port F, port C, port B, port D, and so on. So one port of the microcontroller contains several pins. If you take, for example, the port F as F0, F1, F4, F5, F6, F7, and so on. Okay. Then between the round brackets, we are going to have the functionalities of the pin described. For example, if we take this PF0, we see that we have this ADC 0, which means that this one can be used as analog input, and this is one the analog input number 0, so you can connect a sensor to it. And here you can see, for example, the analog input 1, and so on. But then some of these pins, they have different functionalities, no? So for example, if we take, let's take maybe this one. So here you can see that we have TXD and int3, okay? So this means that this pin can be used either as TX pin for the serial communication, or either as an interrupt pin. So you can repurpose the functionality of the pin as you need it later. And the same is true for example, for other ones. So for example, this one, the number 30, PB6, as an interrupt, has a possibility to do PWM, which is this OC. So OC, and then this one is the ADC. So you can then even use this as an analog input, and so on. For example, this one, it's also used for MISO and MOSI, which means they are used for programming. Okay. This one, RTS, is reset. Then when you have XTAL1, XTAL2 is for the crystal. Then when you have SDA and SDA,
we have two resets, because we have RTS, the pin 12, and pin 13 is also reset.
Yeah, so this means that this one has another functionality for sure. So when you are not sure about this, what you can do is you can go down to the datasheet and you can look each of these things. What does it mean? So for example, if we look SDA, so here, for example, there is a longer explanation. No? So let's take the one that you were looking before. This is functions of port D. The one that you were looking was RTS. Wait a moment. So this RTS pin, I think it belongs to the communication. Is a way to check the hardware flow. So you have the hardware flow control on the serial in this case. And this RTS pin is used for this purpose. So in case, guys, you have some questions or doubts about what a pin is doing, you just do Control F and do a research inside the datasheet, and the datasheet is going to clarify you. By the way, at the beginning, it's important to have some, so to look for some simple functionalities of the pin, and then later on you can see all the advanced use that you can do there with the pin. Actually, all these functionalities are easy to be used using the Arduino libraries. They are more difficult to be used if you're going to program them in C. So I can show you some basics of C also, but personally to my students, I don't recommend to program everything in C. So if they have the background of programmers, they can do that for me, no problem. But in case they don't, I will first start with the Arduino libraries, which are quite straightforward to be used. And then if they like to, we go back to C and we look at more complex stuff and so on. Okay. So questions about the microcontrollers? Okay. So guys, this is just a preview of what we are going to do for the networking week, as just an overview of how we can connect two microcontrollers together. So the microcontroller, guys, are still computers, and this means that they can have a network to which they can connect to. So in this case, the first communication on the top is called the serial communication. It's a very old protocol that we have since the 80s. And this protocol works in a very simple way. It can connect maximum 2 devices per time, so it's quite limited. So it's point to point. And it can work in a full duplex way. What does it mean, full duplex? Full duplex means that you can, at the same time, transmit and receive data. Also, the communication is quite easy to implement because you need just to have 2 wires. One is RX and one is TX. Okay. So guys, here is implicit, but all the microcontrollers, when they have to be connected, to share the ground. So here is not shown on this diagram, but you need always to connect the ground together. Okay. So another kind of communication is the SPI communication, serial peripheral interface. This communication here, it's actually being used all the time that you use your Fab SP to upload the code to your microcontroller. So if you remember when we have to connect MISO, MOSI, and SSK, these 3 pins are relative to the SPI communication. So the difference between the serial and SPI communication is that with SPI, you can have more than 2 devices connected, and the way that is managed is having a hierarchy with master and slave devices. So you have the master device, which orchestrates the communication, so takes care, manages the communication, and then here you can have multiple slaves. So what are the drawbacks of this communication? Basically, first of all, you're looking that you have 4 cables plus 1 cable for the slave select. So this means that you have to have a lot of cables between the microcontroller. Instead, with the serial, we have only 2 cables, guys. This is one drawback. Second drawback is that here, the communication is not full duplex, and only 1 communication can happen per time. So you can have the master communicated with the slave 1, and then you can have the master communicate to the slave 2, but you cannot have the master communicate simultaneously with slave 1 and slave 2. Okay, this is the drawback of this communication. So an improvement of this kind of communication is the E2C that was invented by Philips. And with this E2C, we overcome some of the problems of this SPI communication. So first of all, you can see that we use only 2 wires to connect the microcontroller, so it's having less wires than the SPI. Second, we can have multiple masters here, so multiple boards can manage the communication. And also, here is not shown, but with SPI you can connect few slaves. Yeah, I think it's like maximum 4 or something like this.
Daniele, can you repeat again, please, the last 20 seconds?
So basically, the other difference is that with SPI, you can connect Luis. With SPI, I can connect maximum like 4 devices or few devices. Okay. With E2C, I can have up to 112 slaves. So I can have many more slaves. And then still this uses only 2 communication lines. So 2 wires to connect everything. Of course, still the problem in the E2C is that only 1 communication can happen per time, and it's not full duplex. So can go from the master to the slave, or from the slave to the master. Yeah, there is a hierarchy, as my girlfriend is saying here. Basically, the master also here, guys, orchestrate the communication. So the slaves, they don't have power to communicate directly to the master. The master, it's asking all the time to the slaves. Okay. Instead, with the serial communication, guys, any device connected, so device 1 or device 2, can decide to stop the communication, send, receive data, and so on. Okay.
But also between different masters?
You can also communicate between different masters, of course.
Is there a hierarchy, like a master controlling another master?
No, they are on the same level. They're 2 masters. So my girlfriend is asking here also some questions. Okay. Okay, guys, this is just an overview. Of course, if you have the USB, you can even connect the 2 microcontrollers using USB communication. If you have Wi-Fi or Bluetooth, you can connect using them Bluetooth, Wi-Fi.
I have a question, Daniele. So based on the arrows there, I2C, you can have duplex. Can you have duplex?
No, you cannot have a duplex.
You can't.
No.
So the slave will not talk to the master back.
Yeah, it will not simultaneously. The full duplex is when you have simultaneous communication. So this means that while device 1 can transmit to device 2 can transmit to device 1. Here is the master asks to the slave then can communicate back to the master, but it's only 1 communication per time.
But this happens in a very high speed, right? So
yeah, of course.
This waiting means for us humans nothing.
But still, the communication, if you need, for example, to stream a G code, or if you send, for example, okay, for us, if you just send a string, hello, it's going to be very fast. But if you start sending data, for example, audio data or an image or other stuff, then you're going to see the limitations of it. Okay? But for simple bytes, it's going to be very fast, so you don't have to care about this. So one example of this that maybe I can show to you is the following. So with serial communication, you will find plenty of examples online. I think it's more difficult to find example about I2C. Let me see if I can find it in my videos. Okay, so this one's is an example of communicating with 4 microcontroller boards, which are here on the center. And these microcontroller boards are connected using I2C communication. And each of these is connected using serial to a Bluetooth module. Okay. So what I'm going to do now is I'm going to power on the system using a power supply. Okay. So when I power on the system, what's happening is that here there is one master which is saying to the slaves, please open up the communication with the Bluetooth modules. Okay. The Bluetooth modules, they start the communication. After they start the communication, they are going to send back to each slave the information of the strength of the Bluetooth device that they have detected. Okay. And then the master is going to merge all the data, and then it's going to send back the data to the computer. And this was used because what I wanted to do was to detect the position of an object using Bluetooth. So with Bluetooth, you can have like the strength of the network. And then using this strength of the network, you can do triangulation. So now I enabled my smartphone network. And this is, okay. And those are the coordinates in XY coordinate into space about the position of the device that I wanted to do. So in case, guys, you have very complex system, which you need to have multiple microcontrollers connected to a network, I2C is a very good choice. If you need a fast communication only between 2 devices, then you use I2C, serial communication. Okay. So then I was moving the smartphone, and then was moving also the position of.
Wait, I have a question.
Yeah.
Just wondering, how do you enable those different forms of communication? Is that done in the program that you write in the Arduino?
I cannot hear you properly. Lutz, can you repeat, or maybe
Yeah.
come closer?
He's coming closer.
How do you enable the different types of communication? Do you write that in the program that you write in the IDE?
Yeah, okay, so how you enable them? First of all, you need to make sure that, let me see if I can have still the 32U4 data sheet. Sorry. It is on. Okay. So first of all, let's say that you want to use I2C communication. Okay. So you need to look your chip to see if your chip supports this communication first. And then, okay, this one supports this communication. Then you need to connect the boards using the proper pins. So in this case, I don't know if you can find SDA and SCL. Let me see to check where they are. SDA. Yeah, here. So this one, for example, SDA is one pin of the microcontroller which you need to connect, and the other one is SCL. Let me find it. It's near, my girlfriend is telling me. Here, SCL. Yeah. So you need to connect these two. Okay. So you remember this schema that we had in the slides, SDA and SCL. This is the first one. The second thing that you need to do, of course, as you were telling us, is to enable the communication using the software. So using the software, you can enable the communication. In this case, we can briefly look how to do it with the Arduino libraries. So the Arduino exposes the wire library, which is used to communicate using I2C. So here we can see an example of how to connect. So as I was telling you, SDA and SCL plus the ground in this case. Okay. And then here is quite easy. We say, for example, wire.begin is the initialization of the I2C library. In this case, if we don't indicate the address, we are going to be the master. Okay. And then here I'm saying I'm the master. I request 6 bytes from the slave number 8. So each slave has an unique identifier. And then here I wait to receive the data and to print it. And here, this is the code of the slave. I have, okay, I want to be connected to the network with ID number 8. Okay, so I'm the slave number 8, or with ID 8. And then every time that there is a request, I send this hello string back to the master. And this is the way that we enable this communication with E2C. If you want to use serial, then the code looks different, but it's similar. You have here serial.begin, and you enable the serial communication and so on. But this is something that you're going to see more, guys, in the networking week or in the embedded programming week. Because I don't know if you have any base for software or the Arduino library. So I don't know if I'm talking of something that still you need to. So you first maybe need to know about setup a loop before knowing how to enable the communication.
Well, some of them already started to
program
to play with it. So
yeah,
the libraries we haven't tapped yet, but soon.
Okay, more or less. I don't know if this answered the question. And do you have any other questions about the network, guys? There are a lot of networks. So this one, for example,
So
is.
if you have a question, wait, just.
Yeah.
Like I'm close.
In your slide,
Yes,
in the second paragraph.
Sorry, guys.
Could you explain the last sentence? So second paragraph, last sentence.
Yeah, this one.
Yeah.
Yeah. So the problem of this sentence, guys, is that this one requires 4 wires. Okay, so this means that you need to have a lot of wires to communicate. And I think maybe I was telling you that you can communicate not full duplex. Then I need to specify that this was not possible with only 2 wires, but if you need additional wires, then you can use the full duplex communication with a single slave. So, but still the communication, guys, happens between 2 actors of the network. So if you have 3, for example, actors, like 1 master and 2 slaves, you can communicate with 1 master and 1 slave 1, for example, master and slave 2, not between master and slave 1 and slave 2 simultaneously. Sophie, other questions?
That's good, thank you.
Okay.
Thank you.
By the way, guys, you are going to work more with these communications kinds, or with these networking kinds into the networking week or into the next weeks. Some of them, they can be quite complicated. Of course, this one is just a preview, because then you can have, I don't know, wireless devices like the ASP8266, or you can have the Bluetooth communication like AC 0.5 is a Bluetooth 2.0, 2.1, or you can have like the HM10, which is actually implementing the Bluetooth 4.0 or the Bluetooth low energy, which consumes less energy. That there's going to be a lot of, there is the Zigbee network is another one. There is the NRF on Nordic Semiconductor, which is a radio device which you can use also. In this case, the protocol is like proprietary, so you need to use the specific library for it. I think the image doesn't load here. I can open this one as well. Yeah, this one. There's going to be the LoRa also protocol, which Neil is talking about. This one, it's quite powerful, but requires some effort, because you need to have very strong central network. And then the slaves, they can also be connected to kilometers of distance in city environments. Okay, this is another one. Do we have also this NRF 52, which Neil was talking about in the last lecture? He was mentioning this NRF 52 as well, and so on. So there are plenty of ways of connecting microcontrollers. The important thing to know about these networking modules are related to the fact that you can use them as a black box. So they embed all the functionalities for the radio network into the module itself. From the microcontroller, you have just to send them some basic commands in order to operate them. So you don't. So if you work with Wi-Fi, you don't have to take care of the implementation of the Wi-Fi. So you use just your Wi-Fi module is in a transparent way through the serial communication. So,
Daniele, we have to maybe in 5 minutes wrap up. We have to go to be in the room downstairs in 10 minutes.
okay, by the way, we have only 2 slides left.
Fine. I guess we should continue on a day, right? Because it is overwhelming.
It's very useful.
Yeah, but it's very useful because all these things that are going to come in the future, and it's kind of nice to be prepared, at least knowing what's going to come.
Yeah, for sure. We can do maybe another appointment instead of the next reviews, or together with the next reviews, as you like. No problem.
Great.
So I don't want to also steal time for this week because I know that it's going to be a short amount of time that you have to work with the CNC.
Yeah.
So, yeah.
Because we are here in another building.
Yeah. Okay, no problem.
But we are figuring out.
Yes, we take another appointment. We do another time. If you want to stop now, otherwise I can continue.
No, yeah, we should stop.
Okay.
It was great again, Daniela. Thank you very much.
Yeah. Thank you very much for giving me this opportunity.
Thank you.
Thank you, guys. See you in the next appointment. I will talk with Louis when it's going
let's
to be.
talk about it. I'm going to talk to them as well, see what suits.
Okay, guys, happy CNC milling.
Thank you.
Goodbye. You're welcome. Bye.